Okay, so time to get started. So here's what we were talking about last time. A very quick rehash of, roughly speaking, the last lecture, I would guess. So we were talking about vector surface integrals. The circumstance that arose, we were thinking about how to take these ideas of what we did that ended up with scalar surface integrals, computing things like mass or moment of inertia, what have you, where the integrals are fundamentally scalar quantities that are with scalar integrands and scalar differentials, and they're just all about scalars. So something went a little wrong. Why is the eraser not working? That's weird. Okay. So something went wrong while we were trying to apply those ideas to this computation of flux. It just doesn't fit quite, and you end up with a different kind of integral. You end up with this thing here where you'll notice that the integrand is naturally a vector, and likewise the differential is also naturally a vector. So different things to be worried about, etc. But the computation goes down very similarly, and remember we had all this framework set up from having previously worked out scalar surface integrals, and a lot of it gets reused. And roughly speaking then, if you want to compute flux from a parameterization, we had a handy-dandy formula, and that's nice. What we found, though, is that there is this nasty little issue with orientation. We had to be very thoughtful and careful about, wait a minute, did I parameterize my surface the right way? This is kind of a new problem, or it seems anyway like a new problem compared to vector line integrals, because, well, with a vector line integral, whether you're parameterizing the right way is usually a matter of inspection, casual glance. Just make your parameter go the way it's supposed to go. There's usually nothing to it, right? But much harder to see when you parameterize a surface. It's just not obvious which way things are going. So you have to watch out for whether you might have inadvertently parameterized upside down, right? And of course, the way you tell is by just kind of directly looking. So however your surface is given versus what your parameterization leads to, right? You can just directly compare and ask yourself, are those the same? And the exact details of how you make that comparison depends on the geometry, depends on the language, it's going to be a little bit different every time. But you have to directly inspect and check whether you may have, such as in this case, parameterized the wrong way. Right? And good news, if you have, in fact, parameterized the wrong way, and again, my eraser's not working. If you have parameterized the wrong way, then just toss in a minus sign in the appropriate spot, right? Making sure to put it where it belongs, of course, right? It's not about whether you get the correct number of minus signs in the right answer. Your reasoning has to make sense, and so you have to distinguish between parts of your computation where the orientation is implicit in something that came with the surface, right, versus parts of your calculation that came from, ultimately, how you parameterized. This is where there's the potential for there to be a difference, right? So the ds and the n are literally pointing opposite directions here, right? So that's why the minus sign belongs there. And again, that's, from a reasoning standpoint, that's actually really important. Okay. We did a lot right before Thanksgiving. Watch out for the language. Again, the job of the language here is not to be precise. The job of the language here is to be unambiguous, right? And so things like, you look at these orientations, two possible orientations on this kind of bowl surface. None of them are pointing exactly upward, right, or exactly downward. And yet upward and downward is a wonderful, unambiguous way to very clearly distinguish between these two possibilities. So you got to think in those terms. And then a couple of ending examples that sometimes you don't have to parameterize. Sometimes you get lucky with the geometry in some form or another. So be on the lookout for things like spheres, where the direction of the unit normal vector is something you can just write down, because we love spheres because they're full of symmetries. Right? Spheres are very convenient in certain ways. So your eyebrow should raise whenever your surface is a sphere or part of a sphere or something like that. Right? And then likewise, kind of gotta love planes, right? So they again are geometrically very convenient. And so this example here, we were asked to compute a flux of a scary-looking vector field through a surface which has described by an inequality that involves a quartic, right? So that's a pretty scary-looking example, right up to the point where you capitalize on the geometry. Right? So be on the lookout for geometric good luck and capitalize accordingly. And I think this is where we ended. So thus ends the mad rush of review, and off we go into now new material. So you may recall long ago we were talking about vector line integrals, and I pointed out that there was this weird notation. Instead of writing it as f dot dx, right, you could write it as p dx plus q dy plus r dz, and it kind of sort of makes sense from a algebraic standpoint, but it's intuitively unsatisfying. It's kind of, I don't really like it in that sense, but again, very good reasons, and there's connections to really important ideas. Exactly the same thing happens with vector surface integrals. Now, the algebra is a little different, of course, but I'm going to start off with a computation of the ds vector. We know from previously that the ds vector is, I'm going to say capital N ds dt. Now, a quick pause and aside. Do be careful with your orientation. I have to put the plus minus question mark in here because ds is intrinsic to the given of the surface. N is not. N is part of my made-up, manufactured choice of how to parameterize, right? So this is where this potential, well, I don't know, you might have got it backwards. So heads up on that, right? Now I'm going to ignore orientation issues for the rest of this page, but don't forget to be wary of that point. So anyway, orientation issues aside, ds is in ds dt, and we can look at the formula for n, which I can just write down, which I can write in terms of coordinates, which I can crank out that cross product in terms of coordinates, and sure enough, each coordinate of that cross product happens to be a little 2x2 determinant for which we have an existing notation. Flashbacks to change of variables. Right? And this is when we were doing two-dimensional change of variables, this notation right here, for example, partial xy, partial st. That's exactly how we described the two-dimensional change of variables stretching factor. Weird. Again, with the my eraser isn't working. I don't know why. Oh, no, now it is. Okay, that's weird. Check it out. Wouldn't it be reasonable, for example, to look at what we're staring at here? I mean, distribute the ds dt. Look at what we're dealing with. This is one of our coordinates of our ds vector. It just kind of begs for you to, again, you're a little bit cringy, right? A little bit, this isn't really true. And but it's as if these cancel. And back in chapter 5, we would have felt pretty comfortable calling this dy dz. Right? And likewise with the other coordinates. So we have ourselves now, and again, ignoring orientation issues, heads up on orientation, we have an alternative notation for our ds vector. Again, different algebraic details, right? But kind of tracking the motivation that we gave for writing down coordinates of the dx vector. And with that noted, right, knowing that ds is that thing right there, and supposing that our vector field has coordinates given, let's call them PQR, pretty standard choice. Weird, but standard. making that choice, then just like we did with the vector line integrals, you can crank out this dot product here, and you get this, seemingly suggested by how we've chosen to write the ds vector. So again, we have an alternative notation. Again, not really a fan, right? I mean, you look at your options here. Which of these would you rather write down? Which would you rather deal with? This one down here is bulky. Takes up half the page. It's a little cryptic. What is dx dy when I'm on a surface that's not in the xy plane? What do I mean by dx dy? It's very unsatisfying. Right? So in our context, I think it's fair to say we would never really choose of our own accord to use this notation. So why am I bothering you with it? Well, and again, it's a matter of necessity. This notation right here, very closely related to something called differential forms. That's the same reference that I made back when we were talking about coordinate line integrals. So this is highly suggestive of and closely related to some very powerful ideas, very important stuff that we will not be discussing in this class other than sort of, from a distance. Right? And because of this, it is a popular notation, sometimes for good reasons, right? And because it's popular, that means that you're going to see it, and because you're going to see it, I need you to know what to do when you see it, right? So, for example, our textbook, in fact, will use this notation somewhat. I mean, not commonly, but it'll happen, right? There are some homework exercises where they deliberately choose to write things this way. My advice when you see this notation is to think, okay, all right, well, what an unfortunate choice, but just make sure to realize that what you see here as your sort of integrands, if you will, of your coordinate integrals, that's just code for what your vector field is that you're taking a flux of. And that these differentials, dy, dz, dz, dx, dx, dy, that's just fancy talk for your ds vector. Okay. All right, there's one other little ugly little detail that I need to mention here, especially because of how this integral is written here. Okay, let me in fact circle more specifically. Let me just look at, for example, just this one. Integral r dx dy. That looks awful similar to a double integral. Very importantly, it's not, right? Very importantly, this is still happening on a surface. Right? But if you think in terms of it being a double integral, you're going to have this temptation to reverse these differentials or to feel free to write it down as, I'm going to write it as dy dx instead of dx dy because whatever, personal preference, arbitrary, it seems like it's supposed to be the same thing. In this context, you have to remember that thing, right, this dx dy here on the end, the definition of it is this thing right here. It comes from a determinant. A determinant where the columns, which order the columns of the corresponding matrix are in depends on which order did you write down these two variables, right? So the fact that the x is first and the y is second is telling you about a 2x2 matrix whose columns, the first one corresponds to the x and the second one corresponds to the y. Right? So if you were to switch the dx and the dy, you'd be switching in a matrix which would actually introduce a minus sign. And that's not okay. Right? That's not a freebie. Right? So this dx dy is kind of a loaded thing. It's not quite what it looks like. And in particular, it is very important that the dx be first and that the dy be second. And then notice likewise, and this is the one that tends to bug, right? You see this one right here? Students have a very strong tendency to want to put things in alphabetical order. This one has to be dz dx, because the z has to be first, because that's how this term turns out, because that's how this cross product turns out. There is that minus sign in there, and it has to stay there with the ordering. So heads up on that. Again, you have to just kind of resist the temptation to clean this up and make it look nicer. You can't. It has to look like that. Okay, how we doing? Everybody all right? Welcome back. All right, moving along. So symmetry theorems. This is the time when we were talking about vector line integrals that we introduced the idea of symmetry in line integrals. And big point, it only worked for scalar line integrals. And likewise here, for surface integrals, it's only for scalar surface integrals that we have an odd symmetry theorem. And the good news is it's otherwise exactly the same. So you'll notice the way I've written the theorem lays out on the page. Total copycat, right, of how I wrote down the analogous theorem for several previous analogous theorems, right? Doing that on purpose. The same little NBs down here. You got to watch out for make sure to check. You have to have both of the conditions. It has to be over the same plane, etc. Right? All the same little asterisks. So it goes down just like you would think it does. It's lovely, and I'm a big fan, and I strongly encourage, be on the lookout when you're doing a scalar surface integral. Be on the lookout for the possible very nice convenience of using symmetry. And the same disappointment that while it works great for scalar surface integrals, it does not work for vector surface integrals. If you're looking at a vector surface integral and you want to talk about an odd symmetry theorem, odd being a reference to your integrand, the vector field whose flux you're talking about, there is no odd symmetry theorem. And it's actually not even that hard to see why. If there were to be an odd symmetry theorem, and let me emphasize, this does not work. If there were to be an odd symmetry theorem, I would need, because of the oddness of f, I would need the ds's to be the same on both sides. Which means that I would need for nds to be the same on both sides, which means I would need for these areas to be the same on both sides. Now that's true, right? These areas, little pieces of green there, yeah, those are the same size. But these n vectors are not the same on both sides, right? Easy little geometric appeal. If you have a symmetric surface, as I've drawn here, right? Yeah, the areas are the same, but these normal vectors aren't. And so the whole thing just crashes and burns. There is no odd symmetry theorem. So this is yet another landmine to constantly be wary of. Don't try to make an odd symmetry argument if you're looking at a flux integral, if you're looking at a vector surface integral. There is no such theorem. And again, the danger being that if you claim symmetry and there is no symmetry, then nothing you've written on the page is relevant to an actual solution. And again, that's a nasty landmine to have to deal with. Everybody okay with that? All righty. Okay, so I want to point out there's actually some really strong analogies. I've already kind of hand-waved a little bit toward this. There are very strong analogies between vector line integrals and vector surface integrals. Now, you wouldn't think so at a glance. Vector line integrals are about computing work. Vector surface integrals are about computing flux, a completely different physical quantity. Right? So those are the sort of the immediate physical interpretations or applications, however you want to say it, and that's nice and all. And they connect to the physical world in different ways, but mathematically they're shockingly similar. And we haven't really particularly noticed much of that as we've gone through this stuff. But now that we've got it all written down, I want go through and talk about how strong this analogy is. Now you'll notice I've drawn a line there in the middle. What we have on the left side is objects and equations about vector line integrals. On the right side, we're looking at objects and equations involving vector surface integrals. And you go to kind of a compare and contrast. Mostly compare. Keep in mind, each one of these is a result of a parameterization. Right. Now, confession, I've drawn my parameterization kind of weird here. This was purely a space on the page thing. I just didn't have room to write these parameterizations, fully horizontally like I normally do. So apologies for kind of squeezing. I had to kind of squeeze the target sort of under the domain. I know that looks weird, but that's just a page layout, nothing more. Okay, so given a parameterization, whoopsie, I need that line to stay there. Given a parameterization, we get a derivative of that parameterization, velocity. Or, looking at a parametric surface, we can talk about what I'm going to loosely call the derivative, the capital N vector. After all, this is computed from partial derivatives. Right? And there's a cross product. It's a little, slight difference. But this comes out of a derivative of the parameterization. Notice where these, what I'm going to loosely call derivatives, where they show up in the resulting algebra. Check out the analogy, right? They appear in morally the same places in these equations. Now, okay, related point. There's also the matter of the unit tangent vector and the unit normal vector. Those being just, of course, normalizations of the derivatives, which then also appear in analogous places in these equations. And on down the line, we can talk about the size of a piece of the domain. Let's see here. Oh, gosh. Color choices. I guess I'll use orange. The size of that little piece of curve. The size of the little piece of area. They show up in analogous places. Right? Don't forget we have this fancy object here called the dx vector. That tells us, reminder, everything I want to know about that little piece of curve. The dx vector by its direction tells me how this piece of curve is oriented. The dx vector by its magnitude tells us how big this piece of curve is. Likewise, over here we have the ds vector, which by its direction tells you how that little piece of surface is oriented, and by its magnitude tells you how big. How much area there is for that little piece of surface. And notice that those appear analogously in these equations. So, and then lastly, let's not forget the parameters, right? dt telling you how big your little piece of curve is, ds dt telling you how big your piece of pullback area is, also appearing analogously in these equations. So the analogy is bonkers strong. Shocker, right? This is, like I say, a real eyebrow raiser, right? This is strongly suggestive that even though, I guess, sure, why is this thing not, there we go, okay. Even though, again, I need to be in this mode, there we go. Even though vector and line integrals compute work, vector surface integrals compute flux, and again, the physical applications are different and unrelated, one would argue. But the mathematical construction's really, really similar. And again, note how the analogy just continues shamelessly. We've got the derivative vectors showing up like that. And then let's see here, there's too much coloring in to do, but you can go down this list of equations here, color code the same way that I have there. Again, the pattern is perfect. So I think there's tremendous value in making this observation. It's not, nothing on this page is new. This is all stuff we've seen before, but I think it's just jaw-dropping how strong the analogy is, strongly suggesting that this is not a coincidence. And it's not. And again, why are there these strong analogies? It's because both of these kinds of integrals, deep down, what they really are is integrals of differential forms. Which again, deep water, we can't talk about that in this class, but I think it's valuable to realize that they are mathematically kind of the same thing. You can therefore kind of use intuition that you might have already established for vector line integrals to kind of help you work by analogy to figure out how to get better intuition for what's going on with vector surface integrals. If you're weirded out by the capital N vector, for example, what's the deal with capital N? How am I supposed to think about that? It plays a role just like the velocity vector v. That's the strong hint of how to think about capital N. So useful little comparisons like that. Everybody all right? All right. Okay. Oh, wow. We're moving out. So moving on now to section 7.3. This is another one of these massive sections. It's going to take us a week to get through it, if we're lucky. Tremendous amount of stuff in here. Totally ought to be at least 2, maybe 3 book sections, but it's 1. The book starts with Stokes' theorem, and there's a good motivation for that. I and every other textbook that I've ever seen prefer to start with Gauss's theorem, and there's good reasons for that too. Anyway, that's why I'm going to be doing it a little bit differently from the book. Again, kind of like Green's theorem, there's a context. There's definitions that have to get made, choices that have to get established, conventions that have to be accepted, things like this. So we're going to do some groundwork first, and then we'll be able to state a theorem. I would strongly advise as we go through this that you think in terms of, hey, that's kind of like, that's analogous to what we did when we were looking at Green's theorem. It's going to be really closely connected to what we did with Green's theorem. Okay, so first we need to talk about what the word boundary means. Again, now, loaded term. The word boundary no longer just means the edge of your thing. Right? It no longer means the sort of the fence between set and not set. Right? This is now a new loaded concept. Boundary is now an oriented thing. There is a standard convention here. It is arbitrary. It arguably could have been done the other way, but that ship sailed 150 years ago, right? So at this point, we are stuck and sticking with it, and the rule is, arbitrary though it is, when you're looking at a solid region, and I've drawn here a solid region that, just for fun, I've put a sort of an air bubble in the middle of it. Nevertheless, this is a three-dimensional region, and the rule is that the orientation is away from the solid. Now, a lot of people like to streamline that by saying, well, check it out, away from the solid is outward. Right? It really looks like it ought to be. What's the difference? Why do we have to say away from the solid? Isn't that always outward? Not really. When you look at the inside of the boundary, and keep in mind the boundary now does have these two chunks, right? The boundary surface is not just the outer boundary, it's also the inner boundary. And on this inner piece of boundary, away from the solid is actually inward, I think would be fair to say. So heads up on that. Does this make sense to everybody? Is everybody willing to accept? Again, arbitrary. There's nothing magic about outward, right? Or away from the solid as opposed to inward toward the solid. It's an arbitrary choice, but now standard and not arbitrary. By the way, notice again the analogy. when we were talking about orientation on boundaries as we were developing Green's theorem, there was that temptation to say clockwise. Counterclockwise. Right? And counterclockwise, most of the time, if you're talking about the outside piece of surface, the simple version works. But again, on inside pieces, that simple version didn't work. And again, strong analogy. Yeah.
So when you talk about like the boundary surface, this is like the two normal vectors are for two different surfaces, right?
Well, no. The terminology is I'll say a little unfortunate. But when we say the boundary, I mean all of the chunks of that count as the boundary. And right. So, in other words, if you look at where is there green versus where is there not green, and think of the boundary as sort of what separates the green from not green, right? Then you could call that two separate surfaces, but I'm going to say that it's one surface that has two chunks in it. Yeah. And so we call it the boundary singular, and I get that it would kind of make sense to call it the boundary surfaces, but nobody ever bothers with that. Yeah, it's a good question. Anybody else? All right, so that's what boundary means. No one is surprised, I'm sure, that we're going to be talking about accumulation. Again, that's kind of what integrals are about, right? We're going to be developing a theorem about integrals here, so accumulation is not a shocker. We are going to look at a particular quantity that accumulates over volumes, accumulates over solids. And that is boundary flux. Now, reminder, when I say accumulates over solids, what I mean is that if you have a whole solid, and if you look at the quantity in question, in this case, outward-oriented boundary flux, if you look at the quantity in question for the whole, versus if you look at the quantity in question that you would associate to, let's say, the left piece, and the quantity in question as you would, that you would associate perhaps to the right piece. Accumulating means that the quantity in question for green plus blue gives you yellow. Right? And so the way that boils down in this case, let's look at the outward-oriented boundary flux for R1. Outward would be like that. There's also this kind of flat face here. That's part of the boundary of R1, and outward is like that. Right? Then there's looking at the right half, previously in blue. There's that and this and that. I'm about to have a color problem here, so let me just fix that. So there's the alleged accumulating quantity for the green. Here's the alleged accumulating quantity for the blue. I claim that this actually is an accumulating quantity. I claim that when I add these two together, I get the outward-oriented boundary flux for the whole. And again, it's just sort of noticing that what you have in the middle cancels, right? If you look at the, on this middle face, it is oriented that way as part of the boundary of R1. It is oriented this way as part of the boundary of R2. That's two exact opposite orientations on the exact same piece of surface. And so those cancel, and with those having canceled, it now pretty much immediately noticeable that what is left is exactly the outward-oriented boundary flux of the whole thing. Everybody on board? You'll notice, and now let me flip real quick over to when we saw a sort of a point of view on the two-dimensional divergence theorem. Recall our original take on the 2D divergence theorem was that it's a twist on Green's theorem, turn your head to the side kind of in looking at Green's theorem. But then I pointed out you didn't have to. you can think of outward-oriented boundary flux, two-dimensional outward-oriented boundary flux, as being another accumulation theorem. We drew this picture, and again, sort of the dividing line, and outward away from D2 points that way, and outward from D1 points that way, and again, same edge, opposite orientations cancel. And notice how it just looks exactly the same as this here. It's just that here it's a three-dimensional instead of a two-dimensional. Neat observation. Okay. All right. Is everybody okay? Let me pause again. Questions? Everybody's happy. Okay. So, again, there's this distraction. People think it's weird when you talk about flux as accumulating, because after all, the flux on the outer boundary happens here, and it seems weird to associate that flux with a flux that happens on a boundary of a piece, such as in there. It seems very creepy, for example, to ask how much of the purple flux happens on the green surface. Well, the green surface isn't part of the purple surface. What are you talking about? That doesn't make any sense, right? So, again, this is a distraction. Right? Thinking of the flux as happening on the boundary surface, it kind of does in a way, but it also, you don't have to think of it that way. Don't think of where it happens. Think of what it belongs to. Right? So let's not think about the flux happening on this boundary surface and this flux over here happening on that boundary surface. Let's think of the flux that belongs to this hole, and then ask how much of the flux that belongs to that hole is flux that belongs to that piece. And that's extremely relatable. That's, well, no big deal. This piece is part of this hole. The quantity in question happens on the boundary. Again, distraction. Don't think about that, right? Think about, we have a quantity that accumulates over the whole of the blue, and I want to know how much of that quantity happens on this part of the blue. Perfectly reasonable question, right? Think about any other accumulating quantity. Hey, how many of the ants that I have trapped in this region are actually currently hanging out in that subregion? Perfectly reasonable question. How much of the mass that's in this blue region is actually in this orange region? Perfectly reasonable question. So make sure to think in those terms. Don't fall for the distraction of where the flux is actually computed. Okay. All right. And since our flux behaves like a stuff and has locations, we can talk about its density. And again, it seems pretty weird to talk about flux density, but recall, when we talk about mass density, we're talking about how much mass, let's see here, how much mass there is per unit volume. Pretend like that's a volume, artistically, a little bit harder to represent. But density is this very simple idea of, well, accumulating quantity per unit volume. Mass density is extremely relatable, no big deal. Well, flux is an accumulating quantity too. So I can talk about how much flux, which again happens on the boundary. You're going to have this urge to think of it on the boundary, but it's an accumulating quantity that accumulates over interiors, right? So you can think of how much flux there is per unit volume. In the same way. And so in the same way that we call this mass density, well, likewise, we're going to call this flux density. Accumulating quantity per unit size. Everybody all right? And here, this is the part of the discussion, this development of the theorem that we're aiming towards, where I'm going to sweep a bunch of stuff under the rug. It's arguably important as part of a mathematical calculation. I have to recognize, yeah, sure, it's very important to be able to know how to compute the density that's going to be our integrand. You can just see it coming, probably, right? But for Math219, for takeaway, I think in terms of when I make decisions like this, I think about, okay, what's important to me that y'all retain 5 or 10 years from now? When you look back on this class and having waded through a bunch of details to motivate this formula, it doesn't really make my list of things I think it's really important to retain. I do think it's really important that you retain the idea that we're talking about a flux density, that we're talking about an accumulating quantity, that the orientations of the boundary are ultimately what makes it work. That's what really matters. That's what you're going to use. That's what's going to give you the intuition that will allow you to use these ideas in other contexts. So I'm just going to wave my hands and say that flux density, aka flux per unit volume, is computed by this formula. And you can, if you want to see those details, they're in the book. Go ahead. That's fine. Good, even healthy, right? But it's a detailed calculation. It's not worth class time. Of course, you'll recognize we already have a name for that. We've already called it divergence. We saw that back in Chapter 3. We saw these notations back in Chapter 3. All good. So this is what we're going to need to be able to make use of this idea of flux density. Pausing again. How are we doing? Everybody okay? Yes?
Is this kind of related to the idea that divergence is like a source-ish?
Yeah. Oh, yeah.
Where you can accumulate the fluxes through the sources?
Yes, absolutely. And we're going to totally get to that. Absolutely. Yeah. Anybody else? Okay. So now, reminder. Let's see here, and I hope I'm on the right page back here, but I don't think I am. Yeah, I'm not. Okay, but I'm probably close. Yeah, here we go. Okay, so reminder, we talked about how the fundamental theorem of calculus can be used as a kind of a model for all of these analogous theorems that we're developing. And again, the word analogous is really strong, right? I mean, there are strong analogies here. So as we were developing the fundamental theorem of calculus, as we were redeveloping, right, weird take on the fundamental theorem of calculus, I made the observation that the derivative should be thought of as a density. It's change density where change is an accumulating quantity. It accumulates over intervals. In the usual sense, if you cut the interval in half, like that. And that density doubles as an indicator of where the stuff is actually happening, right? So if you want to know, I see a certain amount of change in this function here, where did the change happen? Well, the fact that the derivative is large there is a pretty clear tip-off that that's where the change is happening, right? And the fact that the derivative is negligible, let's say 0 over here, again, a pretty strong tip-off and a pretty satisfying tip-off that, there's no change happening here, right? The derivative, aka, more importantly, the density, is pointing to where the change is happening versus where the change isn't, right? And we had this explicit example down here, sort of oddly simple, oddly sort of making a mountain out of a molehill here of, pulling out big guns to be able to make the decision about where is there more change happening in the vicinity of 1 or 2. Well, obviously it's steeper at 2. Of course there's more change happening at 2. Right? But I just wanted to explicitly point out that if you want to know where the accumulating quantity is happening, you look at the density into which you plug the 2 points that you're interested in comparing, and just look and see where it's bigger. The density shows you where it is. Right? Now, again, that's in the context of the fundamental theorem of calculus. Let's look back here now. We're talking about divergence being flux density. Okay, well, here we have a vector field. Wow, those are hard to visualize. And we're looking at flux. Oh my gosh, that's a great big monstrous integral thing. It's hard to visualize. Where is that happening? Is it coming more from this point A or this point B? Seems like a really hard problem, right? But again, if you're interested in where the accumulating quantity is happening, look at the density. Divergence is our flux density. Divergence is what we plug into with our 2 points that we're comparing, A and B in this case. If you want to know where most of the flux is happening or where more at one point compared to the other, look at whichever one is bigger. There's more flux happening near the point B than there is at point A. Simple as that. Everybody okay with that? Again, strong analogy to the fundamental theorem of calculus. I encourage you to have kind of both pages open at the same time and be like, okay, so over here it makes sense because, try to get your intuition from the easier picture of the fundamental theorem of calculus, and then all of that intuition, there's the analogous version thinking about divergence and the new theorem that we're hurtling towards at this point. All right, and here's the new theorem. Notice the layout on the page looks exactly like the way we laid out Green's theorem. Again, that's very deliberate because it's morally the same argument. Different details, different geometric context, different details accordingly. So the big idea is that we are going to think of flux, outward-oriented boundary flux, as being a quantity. Not an expression, but itself a quantity. We make the observation that it's an accumulating quantity. The whole is the sum of the parts. It adds up over the interior. It accumulates over volumes, however you want to say it. And then we make this last observation here, if I could decide on a color, here we go, that when you want to rewrite flux, these little pieces of flux, d phi, and you want to rewrite it in terms of volume, dv, that is naturally done by way of talking about flux per unit volume, aka our density. Our quantity in question being flux, therefore this being flux density. Shameless ripoff of Green's theorem. So I encourage you to, again, use whatever intuition you may already have from Green's theorem, and by analogy, help you understand what we're doing here to develop what we call Gauss's divergence theorem, that these two integrals are equal. And let me go ahead and circle this like this. If you are interested in a flux through a surface, namely a boundary of some solid, you want to compute flux for whatever reason, an option is to compute a triple integral over the interior of the divergence of said vector field. Or vice versa, depending on situation, one or the other might be easier, depending. Okay. All right. Let's see here. I'll tell you what, we have 48 seconds left. I don't think that's enough to start this example. So why don't I call this a good cliffhanger stopping point here, and we'll pick up here on Wednesday. Welcome back again. Good to see you. See you on Wednesday. Let's see here.